Go.
Go ahead.
Those. Mr. Unzicker?
Yes, you can go. You're on.
Okay, I'm talking on evidence, the endangered roots of science. And, well, I perfectly agree, I think, with Isaac Asimov. I believe in evidence. That seems a perfectly reasonable statement to me. And I think it's the very foundation of science. Otherwise, we wouldn't gather here. And there is definitely some physics that works, at least the physics necessary for transatlantic video conferences. And my best wishes to the audience from a summer evening in Munich. Hello, everybody.
Hello.
Hello.
And, well, my special greetings to David Dickelster, who invited me to this conference on natural philosophy. What does that mean? Aren't we talking about physics? Are we talking about philosophy now? Isn't physics just the successful part of philosophy, the subsidiary that managed to get out of these debates, to get out of these pointless massaging of concepts, poorly defined concepts we physicists use to mock philosophers? So, shouldn't we just talk about physics? And, but is this science of physics really true? Is this evidence-based science really that successful? And I think there is a danger. And George Bernard Shaw expressed it beautifully: beware of false knowledge, it's more dangerous than ignorance. And I think this is a serious concern in today's physics. Physics has undeniably great success, but this wonderful endeavor of modern physics is also, I think, in the midst of a profound crisis. And in the first part of my talk, I'd like to tell you about what I think is really good evidence for this crisis. Okay? So, I will point out the methodological, sociological, and historical reasons for that crisis of our empirical science, hoping that a proper understanding of those reasons can help to overcome the crisis. Obviously, there are some undeniable facts we have learned about nature, and I think obviously as well there are some misguided concepts that are used to describe nature but are not really useful to go ahead with our understanding. So I call this how to distinguish the undeniable facts from fallacious evidence, where to draw the line, what is correct, which ones are the concepts we can believe, we can trust, and which concepts are not really so good. So where to draw the line, and I realize this is a dangerous thing. Thus, I will start with how to draw the line, and prior to giving my own statements, my own opinions about some concepts of physics, I think we can reflect about the methodology of science. So, what about this stuff of inflations and strings and brains? That's what I definitely not want to talk a lot about this, because I think these are very popular concepts in theoretical physics, but I think these are degradations, multiverses, strings, brains. I don't think this is based on evidence, and I think this is a kind of perverted science. And if we are getting rid of empiry, there is nothing to be gained. Okay, so it's quite popular, and some guys like to discuss if science could advance without evidence, without the empirical method. And I'm even almost ashamed. There was a conference held in Munich about white raster theory, and these gentlemen like to discuss the scientific methodology in the absence of empirical data. That sounds to me, let's discuss scientific methodology without scientific method. It's kind of absurd. And instead of scientific methodology in the absence of empirical data, I think we have another problem in modern science, and this is unscientific methodology in the presence of empirical data. This picture is taken at the press conference where the Higgs boson discovery was announced, and I think that this is kind of a culmination of a crisis in physics, despite the fact that it is based on so-called evidence. Okay, even there are many critics of concepts like string theory, multiverses, and parallel universes, and all this stuff. Yet the majority of the critics, they still believe that the so-called empirical science certainly does make sense, and that's the real or the same part of it. I disagree, and I will try to give you some arguments in my first part. It's quite noisy at the moment. David, can you hear me?
Yeah, we hear you fine and dandy.
Okay, so for me it's fine as well. So I will try to give you some arguments that physics is indeed in a crisis. Look, for example, at the standard model of particle physics. We have up quarks, down quarks, charm quarks, range quarks, top quarks, bottom quarks, 3 colors each, and then mass of gluons and electron neutrinos, muon neutrinos, tau neutrinos, a couple of interacting particles, and so on and so on. So it's a plethora of particles, and I mean, if you start from the point of view of natural philosophy, you cannot really make sense out of this. This doesn't really sound convincing, and I feel remembered, if the Lord Almighty had asked me before embarking creation, I should have recommended something simpler. These were the words of King Alfonso el Sabio of Castile. And actually he said this when he entered the library of Toledo, when he first saw the epicycle model of medieval astronomy, with all these arbitrary numbers, with all these epicycles, with all these concepts that obviously did not make sense. However, it's the standard model of particle physics is widely accepted among physicists, also critical physicists, and I think this, we have run into a mess, bluntly speaking, and Enrico Fermi was right in stating, if I could remember all these names, I would have become a botanist. But I think the major part of the reasonable people, especially in particle physics, they have died, and we're in kind of a desperate situation. Nobody wonders anymore about this complication, and it's certainly a sign of a crisis. I cannot imagine a theory containing an arbitrary number which could have been chosen by the creator in just another way. That was one of Einstein's statements when he, of course, long before particle physics, but I mean, to get to a state of mind, you have to realize that all these founding fathers of physics, they're really reluctant to the idea that we have a bunch of numbers we just can measure, we do not understand. So he really hated these kind of numbers, and in the modern models we have dozens and 53 parameters, not counting even the masses of the standard model. So this is definitely something the actual model is definitely something which would have been considered hilarious by Dirac, by Einstein, by Schrödinger, and I think that everybody who has read a biography of these guys would agree. So I think there is one slide missing here. Anyway, yeah, I think the slide missing was Newton's quote: "Truth is found if ever is found in simplicity, not in the multiplicity and confusion of things." That was a quote of Isaac Newton. And yeah, that's, by the way, a tentative definition of simplicity. If you follow my view that simplicity is a quality sign of physics, just count the number of free parameters, or you might call it also fundamental constants. The more we have, the less we have understood. And that's how science worked in the past decades. We had measurements, and we were continuously introducing new numbers to describe these experiments. But there is no a priori reason. All these numbers were introduced ad hoc. Sometimes they managed to decrease a little bit the number of free parameters, but the progress in particle physics especially was more like one step ahead and two steps back in this sense. The number of free parameters is continuously increasing. So this is one thing I think which is pretty good evidence that we are in the midst of a crisis. The philosophical point of view is nothing is created by coincidence, rather there is reason and necessity for everything. That means that it's our job as theoretical physicists to calculate numbers, to explain things, not just to describe and do this kind of theoretical bean counting, which is popular in today's theorizing. So I don't know if you can you see all the slides, because some slides are apparently missing here.
Well, it could be there are several versions up there. I don't know which one you took when you took the sharing. So that would be.
Yeah.
So you may have. Go ahead. You can switch.
Oh yeah. Can I switch to the others?
Absolutely.
No, it should be the correct one, however. No, it's the correct one. Yeah, I can switch to the PDF.
Okay. That could be too. They have a translator on PowerPoint when they load.
No,
It's coming, don't worry.
I think that's an up question.
This has 57, the other one had 91.
91 is correct.
This one has 57.
Maybe we just had a blank slide.
So we'll be going back to 91.
There's another one too. Do you want me to look for it? Let me try. Can I try?
No, it's okay. I think it's okay.
This one says 81.
Try the next slide and see if it's.
Okay, no, 81 is correct. Okay. Just that some don't show up. But anyway, I know the contents of it.
Okay.
Yeah, I mean, it's the job of theoretical physicists to explain numbers and not just to introduce new free parameters. And I think this is the proper philosophical attitude we should take as theoretical physicists. So the second big concern is besides overwhelming complication is is the suppression of basic problems. There is too much. There are too many parameters, and good physics is simple. That was the first major concern, and the second concern was the suppression of basic problems. We have so many real fundamental problems which are not solved for almost 100 years. And today's theoretical physicists, they seem not to care about. Okay? I have a little list, and I'm happy if you go to these points more in depth in the discussion maybe. But there are contradictions in electrodynamics. There is an infinite energy, for example, if you calculate the electric field of a single electron. So every electron, if the formulas are correct, would contain an infinite energy in this field. We cannot compute masses. I think that's a huge and underestimated problem. Theoretical physics is not able to calculate, say, the mass of the electron, the mass of the proton, and these are the kind of problems Dirac were after. Okay, we consider this as big unresolved problems, and we cannot do it. We cannot even compute mass ratios, which would be maybe easier, yeah? Such as the proton-electron mass ratio, which is 1836.15. We cannot calculate. We can just measure it. Okay. Another thing we cannot explain. We just have to digest these numbers if lifetimes. So the mean lifetime of a neutron decaying to electron to proton. We cannot, and this is a huge problem, compute the fine structure constant. Richard Feynman once said, this is one of the great damn mystery of physics, and every good theoretical physicist put this number up on the wall and worries about. I don't see all these theoretical physicists putting this number up on their wall. I see rather a repression of these problems and an attitude that says, oh, we have so many results, we don't have to worry about any longer about these fundamental problems. Even more at the basis, there is no origin of gravity which is known, no origin why spin is the big riddle, because contemporary physics seems to say that, well, it's just something added to the usual physics, but there is no inherent reason, no necessity why something like spin should up. Okay, there is nothing known about the origin of radioactivity. But why couldn't there be a complete theory of physics which, without any form of radioactivity, what's the real basic law of nature that requires certain particles to decay and others to be stable? Okay, these are questions nobody can answer, but I think these are valid questions and important questions, and we're not doing a good job to science if we don't care about it. Nothing is known about the nature of space, time, and inertia. We don't know why we live in a 3+ one-dimensional world. We don't know. We can't explain the number of interactions. Okay. By the way, I think that the current classification of 4 interactions is something that's just part of the sickness. Okay. And even more sickness, the idea is how to unify these 4 interactions. I think that there is some very basic misunderstanding in the relation of gravity and the other, and maybe electromagnetism. Another favorite problem of mine is Dirac's large numbers. I think this is a very, very interesting conjecture. You might have heard that the electrical force is 10 to the 40th stronger than the gravitational force, and Dirac wondered about the origin of this of this huge number, and he loved mathematics, and he said, okay, but I cannot imagine that any sort of reasonable mathematics can solve this problem, can produce such a huge number. And then when the first cosmological observations came up in the 1930s, he noticed that the size of the universe compared to the size of the smallest structure in the universe, which is the proton, has exactly the same ratio. And this is a deep riddle, and the same riddle repeats with the mass of the particles. And it's completely disregarded and by modern theoretical physicists. I think any theory that really may advance physics has to solve this problem. Yeah. I mean, I can't even be more harsh. If you might phrase it also in a different way. Take the most elementary quantum system, which is a hydrogen atom, and consider the electrical force, and compare it to the gravitational force, the proton of the proton and the electron, so you get this number. Okay, so everybody says that there is a missing unification of gravity in quantum mechanics, but I mean, Dirac's every unification has to produce this number. Otherwise, it will remain pointless bubble unless you're able to calculate this number. So Dirac's idea is the only idea in this direction. So either you follow Dirac and consider this a problem, or you better shut up if you deal with this problem. That's my point of view on the unification of gravity in quantum mechanics. And so we have a bunch of unsolved problems of really fundamental things, and we are not dealing with all these problems in current physics. And this is a very, I think this should make us aware of the crisis of physics. As I said, some of these guys who really found out something about physics, they were well aware of that these problems existed. We will be considered the generation that left behind unsolved such essential problems as the electron self-energy. That was Wolfgang Pauli. And there were also other intelligent people reflecting on the long-term development of science, and Thomas Kuhn, the philosopher, wrote his famous book about the structure of scientific revolutions, and he exactly described that behavior of science we observe today, the sequence of an observational anomaly, something that does not fit in the picture, and then you try to explain it, you fail to explain it, you create a new parameter and say, okay, this, call it whatever, yeah, dark energy, or call it another quark generation. You introduce a new parameter, and the system complicates. Yeah? And I mean, everyone who has studied a little bit of scientific methodology and a little bit of scientific history should be perfectly aware that what we're doing today in the standard model of particle physics, and also in the standard model of cosmology, we are working on a textbook example of this wrong paradigm of ever-increasing complication of the model. So, well, this is another argument. I just tried to show you various aspects of this. I think that what modern physics misses is go to the hard facts. Yeah, Newton put it in the lingo of the day: God created everything by number, weight, and measure. He was not talking about hypercharge or toughness or strangeness or whatever. We have a bunch of fancy properties we attach to these so-called fundamental particles, but the standard model is unable to calculate the most fundamental properties. The most fundamental property is mass, and the standard model is unable to talk about masses. I think that kind of an absurd situation. We're not wondering any longer about the hard facts. We're constructing other stuff like isospin and charmness or whatever. But this is not. This is a degradation of physics, of the physics of Newton, which really changed the world. So Lord Kelvin also, in the same spirit, but when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. Maybe the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science. So what do we answer all these modern physicists? What do we answer to this statement of one of the most important physicists? So again, I think it's missing here. One slide. I just try to get it here. Yeah. Now it's here. Theoretical wishful thinking. Theory has shifted to entirely metaphoric concepts. I give you an example, okay? Physics does not really understand the beta decay, how a neutron disintegrates in a proton, an electron, and maybe in something like a neutrino. But we haven't understood the process. Otherwise, we could have calculated the probability or the mean lifetime. So there is a big riddle covering all this process, and so we invent a name which is called isospin. We say, okay, isospin is something that changes when a neutron transforms into a proton and vice versa, but it's just a name that says nothing. And then we observe that certain decay modes are very fast, and other decay processes in physics are slow. And we call this weak interaction, a strong interaction. Heisenberg, by the way, thought this is nonsense, this distinctions. It's just a misunderstanding of the other interactions in physics. So, but anyway, even if you believe in weak interaction and strong interaction, also this picture fails to predict, and the failure of these two concepts is called strangeness. If a particle is produced by a strong interaction, decays with weak interaction, vice versa, this is called strangeness. And so strangeness is another one of these weird concepts introduced. And now look, I mean, the standard model of particle physics is now, it takes place in a space where one axis is isospin and the other axis is strangeness. How do these entirely metaphorical concepts happen to be the axis of space? So what space? What the hell does all this mean? Okay, we're tempted to ask from a point of natural philosophy, I think, and today's physics usually interpret all their findings in this picture just to back up their concepts, and an arbitrary meaning is given to banal observations. Take, for example, such a sophisticated and hard to detect particle as the Higgs bosons, the celebrated Higgs boson, and the major part of the evidence was just two photons. Okay, it's the most banal effect because literally every particle and its antiparticle decays into two photons. So what? So we are interpreting very rare effects and trying to back up our complicated models. But I think this is a huge Kuhnian crisis, and eventually this model has to crumble. So another sickness of science is there is always a signal illusion. Okay, if we look at the history of particle physics, I mean it's always the same structure. You build a collider with a fairly high energy, and you detect certain events. You call these events with names of certain particles. Then you filter these particles, and you see what's left. And then you filter the background, and you say, okay, there is something left. Okay, and you call this another particle. You know? And now you go to the next round of higher experiments, and you filter again all the results. But I mean, there is also always something left. You can physics, particle physics in particular, can infinitely fool oneself with this kind of method, going to higher energies to clear every poorly understood signal as a new particle, and then just apply for the next round of collider experiments. And my concern is that cosmology is going pretty much the same way. We have wonderful telescopes. These are really beautiful instruments, but I mean, there is of course foreground, galactic foreground, and there is a certain limit beyond which you cannot reasonably observe, even if you have the best observing technique, because it's just too much dust and too much noise in our foreground. Yeah? And I think this is disregarded. So we are developing fancy theories from very faint data, from distant galaxies, from the cosmic microwave background, and we create this picture of the standard model of cosmology, and part of which I think is reasonable, and part of which is an undoubted fact. I'd like to, but part of it has really also gone to the absurd level of non-falsifiability, like inflation. And I think cosmology is pretty much on the same way as particle physics, and this is a crisis with the same structure. It's going to repeat itself, I think. Interpreting non-evidence is also a methodological concern. Okay, I mean, it could be that if you observe that galaxies rotate too fast, that there is indeed some mass which causes the acceleration, but it's not visible. But it's still a hypothesis, and the more hypotheses you pile on top of each other, the frail the whole building becomes, and the more dangerous is our knowledge, and that's the danger of false knowledge, I think. And this is very, very high if you're dealing with a model in which allegedly 95% of the universe is invisible. Okay, I don't think this can be a convincing approach, and a high percentage of invisible substance is postulated by the standard model of cosmology is must be a concern. Once the problem is removed by a feeble excuse, there's no further need to ponder over it. That's a quote I particularly like by Erwin Schrödinger, and I think it applies very well to concepts such as dark energy or even quarks in particle physics. I see also a sociological effect if something is established that, okay, so we're all in agreement, the mainstream is in agreement, so we don't worry about it any longer, that it might be just the wrong way. And this is a huge long-term risk for the development of physics and science. So my aim is another one of my favorite quotes, to teach you to pass from a piece of disguised nonsense to something that's painted nonsense, and talking about very, very poorly backed concepts like inflationary cosmology or inflations in the brain. And sometimes it's useful also to look at the language in physics publications. And so I'd like to read you one little passage from my book Bankrupting Physics the passage that my co-author Sheila Jones has, I think, beautifully phrased. And if you look at the publications, you find certain hints that something is wrong. So follow along as we take a quick romp through the dictionary of scientific battle game. Calling a theory a model means that it's considered temporary and doesn't have the ambition to explain much of anything. By the way, I don't think Einstein ever considered a model. He had a theory. So models, I don't think they have a place in fundamental science in the long run. The same holds for a class of theories, which is never proven wrong by the failure of its members. Thus, many modern theories supply tools and skills, which usually means that we have tools, but we're not using them. If an approach is said to lead the way or to prepare the ground, then you can be sure that it will continue to do so for some time, even longer if hopes rest upon it. What is at rest here is progress. Promising models are not actually expected to deliver on these promises, and candidate theories usually don't know what to become. If a theory is on its way or well established, this just means that the sickness is widespread. If the theory is rich of opportunities, it's probably just poorly supported. When one can always advance understanding, this is still possible even when an idea is too advanced for the same mind. Wherever signs are pointing, them only go to nowhere, and the words toward, trends, and recent developments are misleading terms conveying that nothing specific, much less quantitative, is being predicted. At best, they describe so-called frameworks. Even if a tangible experimental result is utterly absent, a researcher still can read footprints from the data, while signatures indicate that the body of evidence is missing. And now a really hazardous situation for the mind is if data is compatible or consistent with the theory. Apparently, it is unknown to many that no false statement can be deduced from a correct one, but surely vice versa. This is elementary logic. Sadly, this implies that even the most arbitrary nonsense can predict after many theoretical rinse cycles that water is wet. I think a textbook example of this is cosmic inflation, where some see inflation as proven by the cosmic microwave background. It's compatible with inflation, but only after a huge serving of incompatible logic. So just try to find these words. I think that sometimes they give you pretty good hints that something is wrong with this. So, but all these papers are called physics. All this physics is sometimes called evidence. I believe in evidence. I really believe in evidence. I believe that there is a reality out there. But what is evidence? How can we define it? And now I'd like to invite you to listen to a very intelligent sociologist of science, Harry Collins, and think about how your opinions, how your picture of reality is formed. If you're honest, almost everything you know is hearsay. Even if you're a physicist, even if you're an expert in your field, most of what you refer to is hearsay. And so a direct consequence is that scientific mainstream is the most natural thing you can imagine. Okay? It's so natural that from this sociological mechanism, something like scientific mainstream follows, and it's painful and daunting to leave the comfort zone of scientific consensus. Just imagine you're in a conference room with 500 people, okay, and the talks and the debate goes on about this and that neutrino oscillation, okay. Your consciousness almost inhibits you to think about that neutrino oscillations might be nonsense, but because you psychologically you walk off the big conference, you feel terribly alone. So this is, I think this is a very dominant mechanism, a mechanism all of us are subject to, and I do not exclude myself. I think that everybody is dependent on the opinions of others that you trust, and this is one way we form our picture of reality. Now, the real problem is, if you walk out of the mainstream, you use your own brain. Once you stop parroting, it is terribly difficult to evaluate scientific results. Think about it. The work of tens of thousands of physicists is left to you, okay? If you don't automatically rely, if you don't automatically believe the expert opinions, all the work, all the evaluation, all the doubts, it's left to you, and that's terribly, terribly difficult. And this is why we are also often mistaken. Also, we skeptics claim that we are thinking, we are reflecting, we are maybe even more prone to commit errors because we cannot rely to such a broad structure of expert knowledge, which sometimes is correct, even in most of the cases it might be correct, but if in some cases this expert knowledge is wrong, then science is in big trouble, and we have to remain skeptical. I think it's very natural to go wrong and to be mistaken, and for that reason we shouldn't be afraid of being mistaken. There are two other serious dangers. If you doubt everything, okay, if you're going to verify the entire history of physics with your bare hands, so to speak, you will probably not achieve a new result in your lifetime. So you can stop working as a physicist at that point. If you don't believe everything, if you are too skeptical, okay? And on the other hand, if just a part of your reasoning is based on the wrong assumptions, if you believe in something which is just a wrong concept, all your efforts are lost as well. So if we consider ourselves skeptics, we are in a dangerous situation, and I think that's why Oscar Wilde said thinking is the most unhealthy thing in the world. But think about it. This applies also to you, and I can give some examples in which everybody might agree. Okay, everybody maybe is convinced that gravity exists. Okay, and I hope everybody agrees that the very existence of gravity is not evidence for string theory, as some string theorists claim, okay? But these are just the extreme positions. And if we are scientists and skeptic scientists, we do disagree. And I think that you, from my talk here, you can easily get either disappointed because you think, oh, the guy is skeptical in a way, but he's not skeptical enough. Yeah, there are some concepts we shouldn't really believe, and on the other hand, there might be the anxiety of, oh, I have wasted my time because this guy is too crazy. He doubts too much. He might be skeptical, but that might be true to a certain point, but not to that point. So I think there is a narrow line, and everybody of us has to find his own reasoning, and we have to accept that we have different opinions, and but I don't think this is a problem. Okay, so it should not be a problem because so many people were in error. Okay, Einstein was too stubborn with respect to quantum mechanics. Planck didn't realize the quantized nature of light. And Bohr wrote some babble, so to speak, about duality, and Mach, which I consider one of the great visionary physicists, he didn't believe in the reality of atoms. They all were in error. So what? Okay? So I really don't have a problem if one of you disagrees with me, someone who doesn't believe in relativity, and on the other hand, somebody else who thinks that quarks are real, or quarks are a reasonable concept. Okay? We shouldn't be afraid of that, and we shouldn't give other people a reason to isolate us. Okay? I give you an example. A reader of my book, a distinguished scientist of the Institute of Radio Astronomy of the University of Bonn, he wrote me an email and said, "Oh yeah, you're great and you're right, and this had to be said for a long time and so on. But I have to warn you. You mentioned a certain Professor X, and you know that Professor X, he isn't taken seriously any longer by the scientific community." And I responded, "Okay. You know that I think he's a very creative mind, but sometimes he goes wrong. You know what I do? I tell him to face. Huh? But you saying that he is not taken seriously by the scientific community, you're talking about the same community that uncritically for years accepted questionable concepts like dark energy, a community that did not complain about the absurdities of inflationary cosmology. You know what I think about the opinion of this community? I give it the end." So I think that we have to, everybody of us has to deal with these sociological issues of evidence and opinion making, and I think it's even among us critics, it's an underestimated mechanism. Yeah, we even if we are critical towards mainstream science, I think we still like more making friends towards the mainstream direction than to make friends with the other science. Yeah. So on the other hand, my personal experience that I'm becoming I'm becoming more skeptical with time. So anyway, there are a couple of assurances I try to give you. In the sciences, the authority of thousands of opinions is not worth as much as one tiny spark of reason in individual man. That's Galileo Galilei. And Sir Karl Popper, very important philosopher of science, he noted that intellectuals make ideologies out of their theories. Unfortunately, also in physics, many ideologies exist. Who does not follow the fashion easily drops out of the community members, which are taken seriously. And the difficulty lies not in the new ideas, but in escaping from the old ones, which ranify for those old us. Most of us have been into every corner of our minds. That's an economist, John Keynes, but I think that holds true for every science and for physics, of course. Few are able to calmly pronounce opinions that dissent from the prejudices of their environment. Most are even incapable ever to reach such opinions. That's Albert Einstein, I think a very nice statement. And Louis Victor de Broglie, the discoverer of the Broglie waves. If one had taken the ideas of these scientific geniuses, who have been the promoters of modern science, and submitted them to committees of specialists, there is no doubt that the latter would have viewed them as extravagant and would have discarded them for the very reason of their originality and profundity. So I think that we have to be concerned about the modern state of science, and that statement, by the way, is on the website of archivefreedom.net, and that's an alternative site besides wikra.org from the archive at Cornell, and archive is unfortunately pretty much has become a mainstream publication, and it's not. They're really very intolerant about dissenting opinions. I think this is a serious degradation of this once beautiful idea of science. So Louis Victor de Broglie says, to preserve the freedom of scientific research and the freedom of initiative for the original investigators, this is essential because these freedoms have always been and will always remain the most fertile sources for the grand progress of science. And that's not what we observe in today's communities, unfortunately. Thomas Jefferson, freedom, the firstborn daughter of science, by the way. So if we're concerned about freedom, and maybe one has to be, we should also be concerned about science. Insanity in individuals is something rare, but in groups, parties, nations, and epochs it's the rule. That's German philosopher. And he used to be very sarcastic, but I think that applies to physics too. And we're not well advised to consider ourselves the intelligence or the elite of the sciences. I think the mechanisms of Carrot and groupthink, they are well present in the physics communities. And I particularly like a quote by the German novelist Thomas Mann in his novel Felix Krull, the profession of, and he said physicians, but I think it applies pretty much to physicists. The profession does not distinguish from others in the sense that the majority of its members are the usual twerps ready to testify about the non-existent and to deny the obvious. And I think this statement is too harsh. It's in the novel, but actually that's the harsh formulation of what is called the conformity experiment by the famous psychologist Solomon Asch. And he brought together test individuals, and they had to judge the length of the bar X and compare it to A, B, and C. Obviously, it has the same length as B. But these individuals were surrounded by actors who insisted that X had the same length as A or even as C, and people did agree against their proper convictions. Okay, so and if you were able to express a statement or a judgment against your proper convictions, imagine how difficult it is to form your proper judgment, your proper evaluation of scientific knowledge when you're not sure, when you may be on the verge of deciding this is true and that is true. You're so terribly dependent of other people's opinion, of other people's, of your environment's point of view. So that I think every physicist should study this experiment and reflect about his own opinion. So, again, where are we going to go? Undeniable facts versus fallacious evidence. I think these common definitions of evidence, they have led us into a big crisis of physics. I hope I have provided pretty much evidence for this crisis of physics, and I think we do need new standards for establishing scientific consensus. And what's clearly insufficient, and what has proved to be insufficient, if you don't believe the current state is wonderful, a publication in a scientific journal. I mean, that's quite obvious for everybody who has written a review or had a discussion with editors. There is no need to go into details. Obviously, there is no. It's not sufficient evidence. All experts agree. Right? You might remember the example of continental drift, promoted by Alfred Wegener as early as 1912, and it was completely against the mainstream of geology, and geologists mocked him and said he's not an expert, he's not able to express qualified opinions. And one geologist in 1928 said, if we were to follow Wegener's hypothesis of continental drift, all the knowledge we have gathered in the past 70 years would have been lost. We would have to start from scratch. I believe, unfortunately, there are some fields of physics that actually are in the same situation as geologists in 1912, and that might be a very harsh setback for parts of physics, and definitely the agreement of all experts is not a good thing to call evidence. Established within a field, it's the same thing. I wrote it because it often happens that there is serious discussion and voices of reason with very good arguments, and for long times they are almost balanced, and then the field goes in one direction, decides, then one concept is established, quarks are established, galactic black holes are established, neutrino oscillation are established. So you don't open up anymore the box, and you don't question it anymore, and this is a huge danger. It's not sufficient evidence if your best friend is convinced of it, even if he's smarter than you and knows much more about all this, and that's the evidence we still rely on. I remember, okay, all this I think is insufficient evidence, and we have to arrive at other types of evidence. And well, what can I offer? Own perception, okay. I realize every day that there is something like gravity, and there is something like light, and there is something like electricity, and I can use my cell phone, and there is something like electromagnetic waves. Obviously, it's a useful concept at least, but it's very limited, our own perception, and when it comes to make precise measurements, our own perception is certainly not sufficient. I think I can rely on experiments which are repeated so many times that are at college level. You know? Okay. Remember, I'm parroting too. Okay. I cannot verify everything, every concept, every piece of reality I believe in. I cannot verify it by myself. So I have to parrot, I have to rely on, and I try to find reasonable measures of this categorization. I believe that college level experiments that in part I have done by myself, there is something that radioactive decay, you have measured half-lives, you have measured phase transitions, you have observed that you can delay phase transitions by adding salt to water. This and that. These are kind of experiments I think you can believe even if you haven't done it, and it's repeated so many times that it's good evidence. Okay. And I think a very important point is application in technology. I think there is no reasonable doubt that electromagnetic waves exist because everybody has a cell phone, and there is no reasonable doubt that something like a photoelectric effect exists because it's used in every digital camera, and I believe that something that general relativistic time delay exists because I think it's necessary to write the programs in all GPS receivers. I haven't written the programs, but would be still pretty confident that the effect as such exists. Now, what else? What else could I believe? I believe, for instance, that galactic light is redshifted because I had access to the raw data of the slow digital sky survey, and so to speak, I analyzed it with my own hands. I saw that the more distant galaxies, which of course are characterized by its redshift, but they're also by the fainter luminosity. I saw this, okay, and it's pretty clear that there is something that the galactic redshift of galaxies. So here we go. I think that open data is something very important, but you have to distinguish. CERN, for example, to a certain extent also claims that they have open data, and they even claim they have two so-called independent experiments. But it's not really independent in the sense that there is one community, there is much interaction, and there could be lots of artifacts which apply to both detectors. And first of all, or more important than anything else, is that the data analysis in institutions like CERN is taking place in a vertical structure. That means that one group is working on the beam and is performing the collisions, and another group is constructing the detectors and is collecting the raw signal of the detectors. Another group is concerned with triggering or filtering the results. And so you have different levels, and at the very end, all this pyramid, all these vertical structures then claims that they have discovered the Higgs bosons. I don't think that such a structure makes sense. I think that if you want to do big science, maybe big science is sometimes necessary, but if you want to do big science properly, you need to split up, okay? So people in the economy are thinking of splitting up monopoles like Google and Facebook and so on, but you have to split up the monopole of data processing of the huge collaborations, okay? There has to be one absolutely independent group dealing with the beam only, another group dealing with detector design only, a third group dealing with collecting the raw data only. And then every stage of processing has to be done by different groups, and the intermediate results, of course, they have all to be published. And this is a model which I call a horizontal structure in data analysis. And I think this is, in part, it's realized to a certain extent in the Sloan Digital Sky Survey, a very nice project in observational cosmology. And indeed, this is a huge source of interesting results, also allowing also people from off the mainstream to use very good data and to find very interesting results with modern data. But most of the big institutions are far away from that ideal. So let me collect these new criteria. I think they could be useful. Their own perception, very rare college level experiments, application technology, verified by different independent groups. That might be something in between. I don't really believe even if an entire field of particle physics claims the Higgs boson, because they are so closed in their mind box they don't even allow the questions from outside, and there might be an error, as the geologists at the times of Alfred Wegener were in error. But I think when it comes to particles that show up in different fields of physics, such as detectors, I think about muons, for example. The muon has been detected in the cosmic radiation, but it has also been analyzed by atomic physicists and people who are doing spectroscopy, and they are also identifying the muon with muon with the same properties. So this gives a certain confidence. Okay, so that would be one occasion in which I would be ready to parrot, so to speak, if a result is independently verified by very different groups of physics. But yet, the gold standard of evidence, I think, has to become another one. The gold standard has to be public access to raw data and analysis. And I propose something I would call world scientific heritage. Let's try to get another form of evidence, really reliable evidence. Let's use the internet, and I think every experiment that provides evidence for a fundamental concept should be continuously repeated, possibly also with a copy of the original apparatus. I think this is very important, to repeat the original experiments, to collect the data in a modern form. The goal must be to maintain the complete data of an experiment. If there is a selection, filtering, or triggering, it must be a representative set of the complete data. By the way, I think that triggering as such has no real justification for fundamental physics, and it just helps to the big particle physics accelerators to digest their data. I don't think that triggering makes sense. You're narrowing down your view on a certain subset of the result, and that's where the important things might escape. Anyway, if you do, in case you do triggering, please preserve a representative set of the original raw data and make it public. All data must be stored permanently and as completely as possible after every stage of the analysis. I think we scientists of the present, or even the scientists of the developed countries, maybe, we're not allowed to just use these wonderful data and analyze it one time and then discard it. And that's what's going on in current experimental science. I think that's not the proper way to do it. And I propose that every step of the data processing should be justified and documented. Every step of data selection should be verifiable by open source programs. It's not sufficient if you just have the data. Of course, you have to provide also the tools to these data. Every step, elimination of artifacts, calibration, corrections, removal of background, extraction, comparison with simulations, and so on, should be performed by modules and independently organized groups. That is part of the horizontal structure I was talking before, but of course all this has to go online. Every correction has to be clickable, has to be verified in principle by independent scientists using the internet, and all data in raw and processed form must be publicly accessible using standard file formats to guarantee a model-independent analysis. By the way, side remark, I think this model-dependent analysis, one of the most catastrophic developments in modern particle physics, because these experiments, even if they would be public, they're not even useful anymore. Okay, because you're forced to interpret it in terms of W bosons and gluons and whatever, and top quarks, and you don't get a reasonable set of data that could be open to an alternative interpretation. So I think this is really in big trouble, this field, and that's my proposal how to overcome this crisis. Calculability, all evaluation steps must be repeatable, ideally with remote access. But parameters can be verified by any user. That would be important for simulations, for also to get an overview about the free parameters in the simulations, which are not just a few, unfortunately. And of course, reproducibility. The whole experiment must be as transparent as possible, including the use of photo and video documentation. Metadata should be collected, even if considered irrelevant by the mainstream paradigm. They should be recorded at least the time and the meteorological conditions of the environment, and external reproduction of the experiments must be supported by scientists directly involved with the experiment. I think this is how science could possibly overcome its crisis, and I think this would be evidence that really deserves the name. It's still a dream, however, and before realizing that dream, I don't know if it ever realizes. What can we do? I can tell you a little bit about my point of view on several concepts. I think there is a crisis, as I said, and I believe that the real problems are buried around 1930. And this is a personal search for the reset button, so to speak, where physics went off the right track. And, well, an even deeper concern, but this is a side remark, I'll leave the discussion if anybody's interested. Was Newton even wrong in postulating space and time? And this is at the very reason of our problems until today. Anyway, let me give a brief list. I think there is something you might reasonably call like a neutrino. There is some energy that's missing in the beta decay, but given that the entire process is so poorly understood, it really doesn't make sense if you postulate other neutrino species like the tau neutrino, the muon neutrino, or even neutrino oscillations. I think we're definitely at the stage of epicycles in this field of research, even if, well, there is a problem, let's say, with the beta decay, and but we haven't understood it yet. I mentioned already the muons. I don't believe that quarks are a reasonable concept, even if it has entered the school textbooks in the meantime. I think that was a forcibly introduced concept pushed by some theoreticians, and there are so many shortcomings of this definitions, and I recommend a very good book by Andrew Pickering, Constructing Quarks, Story of Particle Physics. Black holes is of course an issue. Do you believe in black holes? Again, here I would like to say, go back to the raw data, look at the neutron stars, at the fast rotating neutron stars, and if you take a closer look, there is a lot of assumptions we put into these so-called observations, and I would recommend to go back to the raw data and interpreting these phenomena. Quantum electrodynamics, a wonderful theory, the most precisely theory tested. That's what I used to report also for a long time, because I liked Richard Feynman's book on quantum electrodynamics, and he's really a great character, and what I particularly liked, he admitted that physics has problems. There is plenty of stuff which is not understood. So these brilliant ideas of Richard Feynman, they led me to just to repeat that quantum electrodynamics is wonderful to test it again. If you take a closer look, it's at least not that precisely tested. It's kind of it's still based on a lot of assumptions, and there are also challenged results and contradictory results. If you go to the papers and look at the 8th or the 10th, how do you say, the approximation of these virtual particles, I believe that there is something very profound in quantum electrodynamics that regards the similarity of electron and positron and photons. And I think Feynman has opened an important door to that concept of similarity. But I still believe that the current form is not very useful, even in particular if it's copied by everybody else. So I notice also that quantum electrodynamics focuses on observations like the Lamb shift and explains the Lamb shift and the anomalous magnetic moment of the electron. That's another a very good tested number that agrees with theory. I admit that, but I still would say that this is a kind of cherry picking that physical theories sometimes do. They take one result, one observed number, and compare it to the theory, and the other, maybe more important number, is left out of the discussions. When we are talking about quantum electrodynamics and the unification of quantum mechanics and electrodynamics, why are we not talking about the fine structure constant, which is the very unification of these two theories, in the sense that it contains the quantum constant h and the electric constants. So I think it's kind of weird. You grab some results which can be explained, and other results you don't talk about, but these might be more important ones. As I said, I believe in the Hubble redshift. I think this is accessible data. I don't believe that this is necessarily evidence for an expansion. I think that's a very interesting interpretation by Einstein and by Decay, but I'm not going into details here because it's in my recent book, Einstein's Lost Key. And then we have other big science experiments like the cosmic microwave background. I think I wrote about the cosmic microwave background. It's as a wonderful observation. Indeed, it seems to be. I think, however, that they have a serious problem with transparency. I think they should be more public, more transparent in their data processing and their background removal. There are some questions to be addressed here. And of course, a very famous recent result is gravitational waves. I think this, in principle, could be a very clean science because you have this criterion of time delay. If it's the time delay of a couple of milliseconds is there, then you can say, okay, it's not noise, otherwise it's noise. There is still something to be confirmed from another field of physics. I think the ultimate doubt will be removed if gravitational waves are correlated with observations from other fields. By the way, that's also what LIGO director David Reitze said in an interview. So cosmic microwave background and gravitational waves, I wouldn't say that we can't believe it, but if you think about our new better rigid standards, I wouldn't count them as really complete evidence. And another example I recently discovered is the standard solar model. I think that this is a textbook example that might be in a Kuhnian crisis, and solar astrophysics might be in the very same situation as geophysics was in 1912, and there is a very interesting scientist which would correspond to Alfred Wegener, and his name is Pierre Robitaille. I think he's a very good scientist, writes very convincing papers, very sound arguments against the standard solar model, and he's completely ignored by the mainstream. This is one another aspect of our current crisis of physics, and one aspect that pointed me to the importance of sociology and opinion making, and that's why I delivered this talk about evidence. I think we have to consider this. There are lots of concepts that have proven useful in ordering things. They easily achieve such an authority that we forget their mundane origin, accept them as unalterable facts. Scientific process is often stalled for a long time by such errors. And I think such concepts that's not directly observable concepts, they might apply also to general relativity. General relativity is a tremendous, has tremendous observations, but sometimes people ask me, where do you see Schwarzschild equations? How do you get Schwarzschild equations in your theory? And I say, okay, there is no evidence for Schwarzschild equations of Einstein equations, so Schwarzschild solutions. They provide some predictions which are verified, which are tested by very good experiments, but there is at the very end we always have to go back to the raw data and compare them entirely to the theory as a whole, not focus on mathematical concepts and believe that they are real. That's called by philosophers, it's called the fallacy of misplaced concreteness. And I don't believe that we can observe Schwarzschild solutions, or we can observe something like rotations in space of SO3 and SO2 models in particle physics. I don't think this is really observable stuff. So again, yeah, that would be again my personal take. I think I am in error in some of these cases. You don't have to be afraid. You don't have to be disappointed. I think Bohr's idea is very interesting, that there might be something wrong with the conservation of energy. Yeah, neutrino oscillations, in my view, are just deep into the epicycles. Muons is something one can reasonably take as a part of reality. Quarks, I recommend Andrew Pickering's book, and QED, take a closer look. The Hubble redshift is real, not necessarily the expansion, and we have some transparency missing in big science, in the big science collaborations, and I already told you my view on this standard solar model. So, to conclude, some of my thoughts you'll find in my book, Bankrupting Physics, How Today's Top Physicists Are Gambling Away Their Credibility, and my views on particle physics are collected here in the Higgs fake. And don't be disappointed if I'm not skeptical enough. Don't be afraid if I seem too skeptical. Just go and discuss if you like now. Thank you very much.
Okay, can you hear us?
I can hear you.
Can you see us?
I can also see you.
There's a few people who stayed in the room. I'd like to maybe start out that way instead of just sort of randomly. We'll get the microphone up here, but I think that is, if you want to look, I think you hit the nail on the head when you say, if you think I'm too skeptical and you're not skeptical enough. because we're probably one of the most, if not the most skeptical group that you've probably ever spoken to. And probably, to half the people in here, you're still half mainstream, or even more than that. And my question to you is, when you say, for instance, you had mentioned to me in conversations with you about, of course, was it Wegener and plate tectonics. Now I would say maybe even a majority of the people in this room are more looking at the evidence for expansion tectonics, and you had said that maybe you had looked in that. Is this, I think, probably one of the curiosities of people like yourself who has some success in the commercial area, meaning you have exposure and you know, a lot of the people here have ideas, and that's interesting. My question to you as a dissident, maybe in a group that's more skeptical than you, are you still open? For instance, I'll give you 2 examples. Expansion tectonics you had mentioned. If you are are you in the middle of examining that, and is that something that you would consider saying, well, maybe that is correct?
Yeah, I'm glad that you raised that question. That's a very interesting point. And when I was talking about plate tectonics, I just wanted to give that as an example of scientific sociology and history, because actually it was an important point. I don't think one can deny plate tectonics, because you just go to the bottom of the Atlantic and look and see the lava spreading out. You have the seafloor spreading. That's what I would call undeniable evidence for plate tectonics. But the tragedy of all this discussion is that there was a competition between expanding Earth and plate tectonics, and we might well have both of them. Okay, so what is pretty much evident for me, because I have a student who has done this by analyzing GPS data. You have these plate tectonics on the level of centimeters per year. Unfortunately, we're separating the U.S. from Europe at the moment. We're going at a pretty high speed of 1.8 centimeters a year. I don't know what that means for future video conferences. But the possible Earth expansion is on a much smaller level. Let's be dry at the moment and quote the conventional wisdom about the Earth expansion. There would be a limit of something like I think 0.1 millimeters increase per year, and I think even mainstream scientists would acknowledge that it's not excluded at that level. We might debate about the evidence. Anyway, the very interesting point is that theories of Earth expansion are related to Dirac's large numbers, and it was Pascal Jordan who in 1952 and 1955 published these books, Schwerkraft und Weltall, which is gravity in the universe, and he made a couple of very, very interesting observations, and I think these are still, it's definitely a valuable field of research, and particularly even one of my special interest fields, because I think that a slight Earth expansion in that range of, we're talking about less than 10 to the minus 10 relatively, could possibly provide evidence for a change of the gravitational constant, and in turn provide evidence for Einstein's important idea of variable speed of light. I fear my answer was too long.
No, I think it's related to another question. I'm going to get you with the hard questions right away, because what happens if I introduce the easy questions and talk and make you feel comfortable? We don't have feeling comfortable in this group is very boring. So
Okay.
here's
Okay.
another.
Let's leave the comfort zone.
I will. Since I'm one of these people here, I'm sure they have some of the same questions. So I'm going to hit you with another hard question. What do you believe when you look at a group like ourselves? If you look at the makeup of our group, we have probably 18 to 20% PhDs. Many of them are not in physics. Most people in the room maybe they have a bachelor's in physics but never used it. Maybe they're not a physicist at all. Lots of them are engineers, which I think that's not unusual because I think engineers have a very, I think, healthy attitude towards science because they don't go for all the, fancy stuff. They want what's real. But I know what's probably on your mind. I'll give you an example. That would be me. I'll put myself right out there. When you talk about the neutrino, for instance, and beta decay, my mentor, Dr. Karazani, has done amazing work on that. And I would say to myself, okay, well, I'd send it to Dr. Unzicker, but a couple of things. He probably gets lots of the crazy stuff. He probably doesn't have a high opinion of our group because we're not necessarily scientists in the realm, so we may be wonderful people painting paintings, but we're not going to be exhibiting in the Louvre. But it doesn't mean that the decades of work here, and I've been around these scientists, that there are some really great work. And not only that, as a community, for instance, an expansion tectonics is one of them. I've seen this community go from a few to probably a majority, knowing and looking at the evidence. And I'm not talking about empirical evidence that you can, but things like if you take away all the seafloor beds, the whole Earth fits together. I mean, that's a hard one to argue. But what I'm saying is, we amongst ourselves have a respect as scientists that we don't care if you're Dr. Unzicker from MIT or if you're a person who lives under a bridge. One of the things I say in my film, Einstein Wrong, was don't listen to what I say, don't listen to me, listen to what I say. And
yeah, that's definitely true.
Yeah, and I think my question to you is, I have this feeling like, well, I'd love to send you Dr. Karazani's work because he's very serious. He has a PhD in physics, and he did an experiment at Stanford Linear Accelerator. But I get this feeling, and I'm not saying it's right. This question to you that if I'll send you that and you'll look at it, but Dave's in supercomputers and maybe he's bright, but he doesn't know what he's talking about. Let me almost like I'm going to get the mainstream response from you. I mean, what is your attitude toward a group like this, knowing that there are people in here that have been working on these things for decades, and it's not, building crazy models of the universe. There are very serious engineers here. What do you say to the people here who said, Dr. Unzicker, you've gotten a lot of publicity. You have some ideas, like you said, that we think aren't skeptical enough, and we as a group maybe want to say to you. You got the question?
Yeah, I think so. Well, I mean, first of all, I mean, I have no problem with dissenting opinions, and nowadays that's one of the big sicknesses in the public debate. Not only in science, by the way, also in politics, arguing like, you have been in a conference with this and that guy. This and that guy said this and that about that. This is crazy, so you're crazy too. Your opinions are worthless too. I think this is a weird argument. I have no problems to respect other scientists with very different opinions. I mean, different opinions are not a contagious disease, okay? I do not necessarily share your opinion. It might be impossible, but of course you can very well have very different views and not believe in something I'm convinced of, okay? So I think we have to get rid of this. That's again a psychological feeling. Yeah, we are feeling good if we are perceiving consent from our peers, from colleagues, from others, but that's kind of we have to get rid of. I think we should respect each other, but certainly I will not I will not believe everything you say, because you're not a homogeneous group. There will be plenty of people, plenty of disagreement among you too, and there is plenty of disagreement between you and me and you and your neighbor and whatever. So what? That's my message. So let's arrive at just at an exchange of ideas. I listen to you, and if you seem a qualified person to me, that doesn't mean you have a PhD or whatever. If you're just able to give reasonable arguments, I'm ready to listen to you. And even if I do not agree with you in the first place, or it could even be a seed from which later something else grows. You know, I mean, the fields where I have become a skeptic, I haven't been convinced immediately that something is wrong. Right? You have to. It takes a lot of time to become a skeptic, and I'm happy to grab evidence and to listen to other people's opinions. It is also true, of course, that can you hear me?
Oh yeah.
Oh yeah, I'm just getting ready for questions here.
It is also true, of course, or you might call it unfortunately, that we dissident scientists are not necessarily the most tolerant ones when it comes to, making friends of our theories. I personally, I struggle a lot with mainstream science because, of course, I have some ideas I consider valuable of Dirac and Einstein's variable speed of light and so on. So I'm constantly fighting with both the mainstream, and I'm also getting very much input. But of course, if I get input which is totally incompatible with my convictions, so I'm unable to devote all my time to it. Okay, so this is also a necessary line of defense. I think everyone should accept and be happy with the statement. Okay, I might come back to your point later, but at the moment I'm not following that road because I'm just dealing with my own road.
Okay, we're going to take some questions here. Those who have questions, just come up. You have to stand up. Use your microphone. Stand in line, please. And then I'd like to try to keep it brief so that everybody get a chance.
Thank you. It's okay? It's working?
Hello.
Hi, Alexander, my name is Slobodan Nedic. We have been in touch on a couple of occasions, so I'm addressing you by your first name. So really I appreciate your work, and particularly the last part that you provide some kind of strategy for overcoming the problems in physics. On the other hand, as David said, this group is really kind of, I feel first time here, it's kind of pretty anti-relativistic, definitely. I myself contributed something really that might be a kind of deep cut into the very fundamentals of Newtonian mechanics and dynamics. In your slide, sorry, is this working?
No, it's working.
I have little problems to understand you. You're talking about the foundations of quantum mechanics or classical mechanics?
Wait a minute. So you had that slide with that demarcation line, right, between area where one is allowed to be skeptical and some limit, some border which one should maybe not cross regarding with too much criticism,
That's
right?
a line everybody has to find
okay.
personally.
Yes. So
Yeah.
by reading your books first in German and later English translation, I saw that you are actually reaching just the level of Einstein and Newton, and really kind of wondering, awaiting somebody of that format to salvage the physics and solve all the problems. So I wondered if you have been looking into solving some problems yourself, and possibly looking to other people who have been working on similar things. So that question and comment maybe is in line with what David asked and maybe what other people would ask. So just including your willingness really to look in some materials. I've been sending you a couple of times my papers, but you did not respond to me, apparently due to your schedule and so on. Thank you. Bye.
Okay, I apologize if I had a little bit problem with the audio. So I encourage you to continue also the discussion by email if you want to be, and not to be disappointed if I'm late in responding. So anyway, it seems to me that you referred to that. It seemed to me that I was you a little less skeptical towards Einstein's relativity. Well, I think that phenomenology, I'm talking about phenomenology, okay, of time dilation and length conversion, okay, let's say time dilation and mass increase, I do believe that. Or you might even say I parrot that, but that's mass increase is something that almost entered the college level. I mean, if you go to a couple of kilovolts in accelerated electron, you already see deviations from classical mechanics. So I don't really doubt special relativity. That's my point of view. That's my take. But if somebody else who uses his own brain likes to draw the line elsewhere, that's okay for me. You know?
Okay, go ahead.
Alex, I'm Cameron Repixel, and hi. It seems that in your speech you said you believe in general relativity, right?
Well, I said the phenomenology, not the theory. I think the theory could be pretty different.
Okay. I just have a question. If it can be shown that special relativity can lead itself to conclude speed of light c equal to 0, will you be ready to give up that theory?
Let me understand your question. You're saying that special relativity would be falsified if what?
If special relativity can show that its own calculation can lead to the speed of light c equal to 0, are you ready to give up the theory?
I give up a theory when the observations do not match. I don't give up a theory if for calculation doesn't work or does not work. That's not making.
Well, in other words,
maybe I misunderstood. Yeah, let me say something. I'm very critical about this mainstream stuff. I think at the very end there is a more profound, more intelligent version of, I call it a version of general relativity, but you might also call it an alternative, which is based, however, on an idea of Einstein itself. It's the variable speed of light theory I developed in my recent book, and it refers to, and has so many, it refers to ideas of Robert Decay and Schrödinger and Dirac. I think this is a pretty nice picture, but I don't believe that the current formalism is really correct, especially if it comes to cosmology, where there are so many things that do not fit. Anyway, you can, however, go to another stage of skepticism and doubt and ask if it's really the case that the more constants we have, the less we have understood. So what about the constant, the so-called most important constants of H and C? And a fear of mine, I wouldn't call it a theory, but it's more a terrific a terrific point of view because it would destroy almost everything of modern physics if C is also an anomaly and H is also an anomaly. If these constants are just a workaround to describe the anomalies of Newtonian physics, that would be really terrible.
Okay, let me.
Why?
Terrible, why terrible?
Yeah,
Yeah.
Oh, man.
because from Newtonian physics, there is no reason whatsoever that particles couldn't be accelerated to ever higher velocities. So why is this impossible?
Could
Okay?
I-
So if you start out from Newton, you run into trouble, and the trouble is called the phenomenology of special relativity.
Good,
And at the very end, it could
Good.
turn out that it's a misguided concept just to use the and all this theory of relativity.
Okay, can I make my question even shorter? I'm sorry. Can I make my question even shorter?
Yeah,
Okay.
yeah, maybe I misunderstood. Sorry.
No, that's okay, you did. You got it.
Special relativity assume and conclude C has a constant speed, which is 300,000 kilometers per second. But another part of it can lead to proof that C equal to 0. In other words, special relativity's calculation is self-contradicted. And if this is shown with evidence by its own calculation, will you be ready to give up general relativity?
Special.
I wouldn't phrase it that way, but you rose an important point. The so-called constancy of C in the special theory of relativity refers to different inertial systems. The theory says that C does not change whether you're an observer in the moving train or you're an observer at the platform. Okay, so two systems which move with constant velocity are physically equivalent, and from that, if you switch the systems, C does not change. But to claim C is constant is a little bit misleading, because the special theory just assumes that this switch of perspective does not change C. It does not say, and that's what Einstein in 1911 also stressed, it does not say that C cannot be a function of time and place. I think that C can well vary, could be a function of time and place, and yet appear as a constant if you just switch the perspective and go to another, with a Lorentz boost to another inertial system.
Okay, thank you very much. Because there are many people behind me, I have to let them get the opportunity. But on the other hand, I will ask David to do me a favor by sending you some short paragraph showing that how relativity will lead to the speed of C equal to 0. Okay, thank you very much.
Okay.
Thank you for the opportunity.
Hello, I'd like to introduce myself to you. I'm Dr. Charles Lucas, PhD in theoretical physics with many honors along the way. My talk here at this meeting was trouble with physics and the solution according to logic and meta theory. And I gave logical arguments showing that first, all the known major theories of modern science, modern physics, that's electrodynamics, Maxwell's electrodynamics, quantum mechanics, Copenhagen version, special relativity, general relativity, and the standard models of elementary particles are all known to be incomplete, incompatible with one another because by logic they cannot be combined under the superposition principle, and that no two theories can use the same fundamental constant such as C, and all of them use C. And so I showed that logic only leaves one solution to progress in modern science, and that is that all of modern science needs to either be done from scratch, or the version of electrodynamics we have needs to be made more complete and replace all the other theories. My question to you is, do you believe that logic, the role of logic has been removed from the scientific method that existed up through the time of Newton, from the time of the ancient Greeks to the time of Newton?
I almost agree perfectly with you. You might wonder. Let me make a few points. Well, we have different theories in modern physics, and I think, and you correctly mentioned they do contradict each other. I would say that we should, some of them we should take them for a while as useful approximations. I think that Maxwell electrodynamics is certainly a useful approximation because it led to the discovery of electromagnetic waves, okay, but certainly it's not a complete final theory because it would have to account maybe for the variability of C, and it's the very same C that had to be used in electrodynamics. But okay, electrodynamics is a fairly good intermediate theory, so to speak, in terms of usefulness. The standard model of particle physics, on the other hand, I think is completely useless baloney. Okay, it doesn't even provide any technology or whatever. It just provides funding for the big institutions, but there is no real outcome. And so I would qualitatively I would make a difference between some of the theories you mentioned, and quantum mechanics is certainly. I mean, what's the big achievement of quantum mechanics? I think people, I'd like to phrase it like this. The beautiful discovery of Niels Bohr that the quantum age that had been discovered by Max Planck played a significant role in atomic physics. That was a huge discovery, and it led to the elimination of a fundamental constant, which is always a major progress in physics. Because the Balmer's, the Rydberg constant, which had been determined by Balmer's experiments in 1885, was now explained and calculated by other constants of nature. And that's also, and for that reason, I think quantum mechanics is a huge step forward. And so was electrodynamics. By the way, electrodynamics unified the electric constant and the magnetic constant with the speed of light. Okay? So instead of three arbitrary numbers, you had two. That's a big achievement. Hey, so far, the general view is that we have these theories, and unfortunately these theories are incompatible, and that's where I agree with you. And I see a deficit of logic. And if people are talking about a possible unification of general relativity or quantum mechanics or whatever, I don't believe that any of these attempts is useful or makes sense. I would rather believe, and this could be pretty much your line, that I would rather believe that all of modern science has a problem that comes from the unreflected postulation of a three-dimensional space and a one-dimensional time flowing in it. And this paradigm is maintained also by general relativity. It doesn't really change the very concept of time and space, okay? But time and space may well be just the most appropriate concept for human perception instead of being really fundamental quantities. And I think this could be the root of the problem, going back to Newton and destroying a big part of modern science. Yeah.
For your information, I'd like to tell you I've published a book called The Universal Force, Volume 1, And in that book, I follow Newton's guidance in mathematical principles of natural philosophy, which said you should use a complete set of the empirical laws in a field such as electrodynamics, and use the complete set to derive a more general version of the force in that particular area. So Maxwell used 4 of the 6 empirical equations of electrodynamics. He did not use Lenz's law or Lorentz's law. And I used them, all 6, and obtained a superior version of electrodynamic force, which includes not only radial terms and velocity terms, but also acceleration terms and radiation reaction terms, which are missing from Maxwell's electrodynamics. From that, I derived the force of gravity as the force between vibrating neutral electric dipoles, and I showed that I was able to predict the value of G from pure theory, no comparison with experiments. I was able to define the electromagnetic definition of mass, of gravitational mass. I was also able to derive the force of inertia and define the inertial mass. And I was able to show that the force of gravity that I derived leads to the quantization of gravity, including this prediction of Stanley Dermot's version of Bode's law. So I was able to show the quantization of gravity, which no previous theory has done. I was able to show, in the case of inertia, the explanation of Eric Lathwaite's experiment, which you may have seen on the internet, where he speeds up a high, very heavy gyroscope, and with one hand, a 3-foot long pole, is able to lift it above his head with very little effort, but he couldn't lift it with one hand when it wasn't spinning. And so you see, and he has one where the Christmas lecture at Oxford where a small boy does it, and he's standing on a scale. And the question is, how could he lift a 40-pound gyroscope without showing any weight on the scale when he's moving it off his head? And so that's the other thing. I was also able to predict all of the major astronomical phenomena for which dark matter and dark energy was, and I was able to predict what's called the modified Newtonian dynamic formula of Milgram, but directly from electrodynamics alone. And I was able to predict the expansion of the Earth from the decay of the force of gravity over time, and was able to show the mechanism. And so those are just some of the things, but it looks like using the NIST data, which was just measured recently to 8 significant figures, there's no longer any nuclear data that can support the strong interaction, the weak interaction, beta decay of a neutron, no neutrons in the nucleus. But we are unwilling to recognize that data, because when we made these theories, we had 4 significant figures, now we have 8 significant figures, and we can't satisfy conservation of energy and all these principles with the data that we have.
Yeah, I think I agree with you that there is a much deeper connection between gravity and electromagnetism. I think that's an important point. And I would be careful to explain everything. As somebody once said, don't explain all the evidence, because some of the evidence is surely wrong. But in any case, I like your method, because your method seems to be go to the original papers, go to Maxwell's publications and see what he has written. I think that's definitely the right approach. Yeah. Thanks.
Okay, next.
Dr. Unzicker, my name is Bruce Nappy. I'd like to talk to you, ask you a question about the World Heritage database, or what did you call it?
Yeah. Of scientific knowledge, yeah.
Yeah, we're right. Now that the one that you described is really a prospective one. It's for current. It actually describes what we might do for current experiments and experiments going forward. What I think, and it's really a request for you to think about writing, is how do we go back in time and capture the most significant experiments that are done. In order for people like ourselves and new people coming up to go back and start from basic principles, it would be helpful to have a similar list of things that you suggested, that we would all then be able to go on and set up a large heritage for the past history.
Yeah, I made kind of that list. It was when I had a debate with a CERN physicist, and he said, "Oh, we would like to put our data on the internet, but it's just impossible. We are producing too much data." And I said, "Sorry, whose fault is it that particle physics grew to a nonsensical size? Whose fault is it that you can't handle the data anymore in a scientifically repeatable way? So just be more humble. If you can't put the LHC data on the internet, just take the LEC data, take the HERA data, take the other collider data, put it in the internet." I would love to see Hofstadter's experiments. I would love to see Lederman's experiments on real neutrinos repeated. I would love to see the scattering experiments at the very beginning in the 50s. All these, but all of it, there is nothing on the internet. There is nothing, not even in a museum, and there is nothing conserved in its pure and original format. And I think this is a scandal. Yeah.
Sure.
I think we ought to conserve, and we ought to repeat these crucial experiments.
Sure, and why it's needed is I can't tell you how many times I have to describe to people the real results of the Michelson-Morley experiment, because they always believe null meant zero, and when you go back and show them the true result, then they stop and they open their eyes. It's
Yeah.
critical thinking.
Yeah.
So a list like that published somewhere would help us. Thank you.
Thanks. Good
Yeah,
suggestion. Yeah.
Hi, Dr. Unzicker. I'd just like to say thank you for a wonderful talk, and yeah, I loved your suggestions for new criteria for science, and also all the quotes you used too were right on target, I thought. And I have one issue with like Thomas Kuhn, I guess, is that I think he misses the bigger picture that I think you understood, that technology is really what is where the scientific paradigm shifts begin, and I'd just like if you could speak for a minute about that role of new technology and how you arrived at those criteria, those new criteria for science of specifically the public access to the data and analysis, and yeah.
Yeah, I think there is a very interesting and very important co-evolution of fundamental physics and technology. You know, I mean, Newton's theory revolutionized the picture of the cosmos, and due to Newton's law, we were able to push satellites into the orbits and put our telescopes into the orbit, which in turn are able to test the Newton's theory with an unprecedented accuracy. Okay, so at the very end, the technology based on Newton's theory helps to overcome his own theory. I think this is a nice aspect of technology. It's surely also in other fields. I also think that that's a crucial role, and that's one of my critics of particle physics. I would say that, well, something like the photoelectric effects, you have it in every digital camera, but something like a tau neutrino and the Higgs boson, and also a top quark and a W boson, they don't have really proved its usefulness and its applicability without the narrow field of academia. And this is a serious problem, because I also think real progress in the sense of a black swan that changes everything, you know? That these events that Nassim Taleb, the philosopher, calls black swans that change the history of humankind. Yeah? Physics has has provided these black swans by quantum mechanics, by developing the laser, and so on. I think that a really fundamental discovery in almost every case leads to an advance in technology. Let me give the sad example of the atomic bomb. But I mean, to the very least, the concept of a neutron that disintegrates makes sense. That it's something that works, even if it had terrible consequences. Okay, but I think technology is an important test, and a test that the past 60 years of fundamental physics failed to do. Yeah. Is that? I feel that there was something unanswered of your question I may have forgot.
Yeah, just like how you arrived at those new criteria for science. Yeah, and like, I guess maybe the role of the internet in creating better dialogues between the different fields.
Yeah. Now Thomas Kuhn was perfectly. I mean, I think there are some things for which you could criticize Thomas Kuhn, maybe, and by mainstream scientists he's criticized who you are. You're using cars and you're using electric lights or whatever, so you're not qualified to make such dumb statements about science. That's a criticism I had about Thomas Kuhn. I think it's totally inappropriate, and I would say he made it's not a complete correct theory of the process of science, but I think he made a very important contribution that to this day is underestimated. Yeah.
Now, yeah. How you doing?
Put your
Very good. How you doing? Very good. Unzicker, I would like to chat with you over my computer at home at a time when you have a time to do that, and I want to send you some work that I have done. Ich bin nicht Missionsdirektor. I have a quote that I want to quote Wolfgang Pauli. Wolfgang Pauli said, ich habe nicht dagegen, wenn Sie langsam denken, Herr Professor. Ich habe etwas dagegen, wenn Sie rascher publizieren als denken. That's what he said.
Yeah, I know that quote. Yeah. Should we translate it?
Well, what he said, I'm going to translate this to the rest of the group here. I have something to do. I have nothing against
slowly, I do object if you're publishing faster than you're thinking.
That's right.
Wasn't that?
But you publish faster than you think. There's something wrong with that, right? And I want to warn people about this. But I would like you look at something. We talked about, the gentleman mentioned something about the atomic bomb. And I managed to do a calculation, the water drop model. You take the nuclei and you calculate the water drop model. When nuclei split, you have barium and krypton, and you have an atomic bomb, right, from uranium-235. And when these things split up, you have two nuclei that are positively charged. And what happened, you have potential energy. And what happened, these nuclei want to get the heck away from each other, and they will repel each other. And the energy that's released when you have two nuclei repelling each other, you calculated exactly 230-some million electron volts. You get the same energy that you would get from relativity. I managed to do that. I want you to take a look at that. And there's another thing I want you to take a look at is the gravitational lensing at the solar lamp. And what I calculated, I managed to calculate the minimum energy path of microwaves going through the solar lamp. And all of these experiments that have been done over the past, let's say, 25 years, to use Mariner satellites to calculate and to receive the energy from Mariner satellites, and also using the extragalactic pulsar system and galactic systems that send out microwaves. And what they found out, that these waves actually deflect at the solar limb at minimum energy parameter, the impact parameter. You have the Stokes parameter, right? The Stokes parameter, that's the nearest path the light goes through, to pass by the center mass of the sun. And they found that it's exactly at the solar limb, but not in vacuum. and there is no evidence of bending of microwaves in vacuum. That's a direct violation of relativity. You should take a look at that and take a look at the I managed to calculate the equation for the minimum energy of bending of light. I come up with the same equation as relativity. It has nothing to do with relativity at all. So I'll let you take a look at that. And if it's possible, maybe at home on my computer, we can discuss this. And I have a paper in German that I'll let you take a look at. I managed to calculate all these things. And I calculate the effects without using relativity at all. And I come up with explaining the experiments and observational evidence without relativity at all, using the emission theory. So let you take a look at that. So we do that at some time.
Okay. I think there are 3 points I hope to get all of these. I mean, I start with the last one. So if I understood, you're challenging the current wisdom of light being deflected by massive stars, such as the sun. And you suggest that this is interpreted in terms of, well, usual optical effect of bending.
What happens is you have the gravitational gradient of the sun. The gravitational gradient of the sun acts on the solar plasma of the sun, and the plasma has a gravitational profile. And when radiation propagates through that plasma, the gravity does not interact directly on the waves. The plasma interacts on the waves, but however, the gravity interacts on the plasma, and the plasma interacts directly on the wave, but the gravity interacts indirectly on the wave. That's indirect so you have indirect, and nobody's done that before.
Well, I'm not really qualified. I think this is a valuable conjecture you might follow.
Yes.
I would say, well, the next thing that comes to my mind is that we have to be careful taking for granted knowledge coming from, which is established, so to speak, in other fields.
Yes.
And the other field in that case is the standard solar model.
Right.
And what I mentioned is the work by Pierre-Marie Robitaille, I think, raises serious doubts about also the existence of the chromosphere in its current form, which is believed. And I don't think that it has this incredibly high temperature of millions of degrees instead of just 6,000 degrees of the solar surface. That's one of the big points he makes explaining this without. Anyway, well, I can't agree, but I don't think this is it's completely wrong what you're saying. I think this is a valuable thing you might follow.
The reason why I want you to look at it, I'm the only one that did this calculation before. If I can get someone else to do the calculation, that'll make me work for you. And I thought you would be the person to do that. If you know someone, I'm take with you sometime.
Okay, we'll have time. We'll have time for you.
As I said, don't be disappointed if you feel some similarity with my views, and I struggle with the rest of physics as you struggle. We're not. Well, it may be cruel to say, but I'm alone with my ideas, and probably each of you is also alone in taking that, making that important battle. What I wanted to make to say before, I don't know if I got it. You talked about the model, the water drop model of the atomic nucleus, and if it was useful for. It was certainly useful, even if I call the model nothing fundamental. But let me be, I think that, I mean, the discovery of nuclear fission as such is certainly something fundamental.
Right.
The development of the atomic bomb is something that is more technology than physics. And I think, by the way, it played a very important role for the importance and for the very paradigm of physics. I think the atomic bomb changed not only the world, but it changed also science. It helped to turn physics, to turn away from natural philosophy to become technology. And that's what we should think going back.
Thank you very much.
Okay, we have 5 minutes before we are stopping, so let's try to make anything as brief as we can, okay?
It's me again. So your previous comment on the gravity technology, Newton theory, and usefulness for this kind of space program and so on, wanted to suggest to you, actually, first to accept your invitation to get back to Newton, starting from the space and time concept, but scrutinizing the very basic assumptions and basic theory. So, Newton theory needs postulation of dark matter, for one thing, and maybe Pioneer anomaly has remained still unresolved. So, I have really kind of here now that there is a chance somehow to communicate directly more the results. So, I am directly here debunking the very basic formula for gravity and the fitting of elliptical orbit to just one central force proportional to r squared. By that, in that way, I actually am reaffirming the Leibniz two-componental acceleration of 1 over r squared and 1 over r third, and it turns out that those laws for the attraction and repulsion apparently apply for all scales in nature. So, I mean, if I'm not, if I may not have interested you much, I would send definitely you once again the paper, right? If you agree.
Okay, yeah, you can send me. Since I had difficulties with the audio, I would ask you. Yeah, I believe you mentioned dark matter, and well. I don't think it's the right place to outline this idea of space and time being the inappropriate concept. However, yeah, I think there might be a very profound problem.
I mean, Newton has started with the concept space and time, but later it has been kind of misused or whatever, you know, with special relativity. Get back what Newton started with. Formula for gravity. Yeah, Newton has.
I can't hear it really. You're saying that the concept of ether.
Okay, Newton hat begonnen mit der Formulierung der Kraft, der schwere Kraft, ja? Und dann hatte er ein Resultat produziert, dass die Kraft in der Form of inverse Proportionalität zu Abstand eine elliptische Bahn herstellen kann.
Okay, ja.
So.
Ja, man kann das verfolgen.
Die sind falsch. Die, in meinem View, scheint sich falsch herausgestellt zu sein.
I follow with interest alternative explanations for dark matter because I don't believe it's real, and there seems to be an interesting connection to the Cayley anomaly. However, you should also note that there appears to be a conventional explanation.
Yes, and the conventional explanation, if you may allow me, turns out to be changing of linear momentum of the closed system, like MV, as though a sailor is sitting in his boat and it's blowing in the sails and the boat moves. I have here proposed the thermal component as anti-gravitational, and then again one German guy in support of Engels, who was first one to say, okay, if there is gravitation, there should be anti-gravitation, and it should have form of kind of thermal. And really, this becomes pretty much consistent. So I mean, just okay. Enough.
We need to pass to the next one.
But
This is the last question, Alexander.
Hi, thanks for your talk. I love your list of how to evaluate evidence to try to overcome sort of the pathology of the sociological aspects of current physics. So one of your slides had this idea that I found out on my own, that I spend most of my time deconstructing physical concepts that just become part of my being, right, about gravity and everything. Do you, and so I'm sorry to say I haven't read your books, do you go into sort of more the epistemology of how to go about evaluating physical concepts, or do you have any thinkers that you like where, you know, you can sort of start analyzing physical concepts from the idea of concepts, how to weigh, how to compare characteristics, etc.
Well, I consider myself in first place as a researcher. I'm just interested in how nature works. So I found much of modern science unsatisfactory. So as a side effect, I've become a critic of it. But in first place, I'd like to develop my own ideas and go back to the papers. I found it always much more interesting to go back to the original publications. And I think I have shown that there are many undiscovered connections of very valuable ideas of Dirac and Einstein and Schrödinger and decay. And that's my basic interest. And I've become a critic of mainstream science just, well, to be able to defend myself against the arrogance and how to explain neutrino acceleration if this cannot be true because we all know that dark energy is established now, yeah? I mean, you have to struggle with these arguments. And, well, so my second profession in dealing with physics is to do this critique. But in the first place, I think I'm a researcher, and I'm a researcher as you. And referring back to the earlier question, what I think about this kind of research of the mainstream and of this kind of conferences, I mean, of course, we cannot be right altogether because we are so different. So the most likely option that is that I'm wrong and you are wrong, and maybe all of you are wrong. But I'm also convinced that if science ever advances, it will be not those tens of thousands of mainstream guys. It will be one such off mainstream guy who makes it eventually.
Well, that's very encouraging. That was a wonderful way to stop this. Let me just say this: your discussion and your coming here has caused so much interest. Lots of them are leaving and already fighting over outside of because they're very stimulating. People are very appreciative, and what I actually heard here today is that they think you are very brave in two senses. First, you are taking on the biggest, how do you say, political and power in physics, which is mainstream particle physics. And that's to be very much commended. And I think you've gained a lot of respect for the, actually we have at least 5,000 people we know working outside the mainstream, and universities are on their own. So there's a great respect for you and your ability to have gone so far. And to say things like when I discuss with or debate a CERN, somebody from CERN, those things in itself, just the act of those things, we know, since there's so much, how do you say, shutting off of these kinds of ideas. So there's a great admiration besides your knowledge and your books. There's also, The second thing that they are admiring is that you would come up in front of a group like this, which makes you look very conservative and mainstream at times. So they think you are very brave for that same reason. But certainly, it's greatly appreciated. You really, this is our last full day. Tonight we have our banquet. Maybe, I'm sure many of them will talk about you perhaps in the future being able to come to one of our conferences and be here. I think that would be really wonderful. So I think it really added a lot. People are very appreciative of your time, and we'll have a recording of this. This is being recorded in several ways. But thank you so much. We're going to go on with our conference here, but you certainly are greatly appreciated. You have a lot of people out there who are very admiring you because of not only your knowledge, but your ability to not be afraid and stand up, because that is absolutely not an easy endeavor. So congratulations and thank you very much.
It was a great encounter. Thank you.
Okay, we'll see you. We'll let you go to bed. Auf Wiedersehen.
Okay.
Okay, all right, folks. We do actually have one more talk. It'll start at 4:20, and we'll go to 5 o'clock. After that, we're over there. We will have a banquet, and we will be moving some of this over because Ron Hatch will be talking, and of course, receiving the Lifetime Achievement Award. So we expect him to have an amazing talk, so that he deserves the award we're giving him. So I don't want to put any pressure on him, Ron. So,
You didn't.
well, they've been instructed to like whatever you say.
So the top, David?
No, it's right. It's the room right down here.
Yeah, the top is here or there?
Huh?
The top will be here or there?
No, everything will be in the banquet room. Oh, the talk right here. The next talk will be
Be right here, eh?
right. Him. There it is. Yeah. I'm gonna go get the paper, which is right. Yeah, at 4:20.
Yeah, and what I liked about it was the U.S. He represents thinking U.S. Some of the lyrics
I enjoyed your talk very much.
Thank you very much. Good support for me.
I know what it is. You need to latch on.
I know exactly. At least I knew that you could see or kind of relevance.
Yeah,
no
doubt. It's probably another false flag. They're probably the CIA.
Good, this guy.
straight up.
Yeah, that's crazy. Yeah. I'd rather have a good crook in there like Hillary rather than Trump, you know, stick an ass. Yeah. Think so? Oh, yeah, she did that sort of stuff. She made a mistake. She didn't do it to, you know, undermine the country. Yes,
And I enjoyed it so much. Like,
yeah, that's
several other people did really good.
well, yeah, you can tell. Yeah.
Yeah.
He changed what I'm going to say tonight.
Oh, that's great. That's very good.
Yeah.
So are we meeting downstairs in the restaurant, or are they bringing it up? It's the room next door. Okay.
I haven't seen it.
Looks like a little nice one. Pretty good. I've enjoyed it.
Yeah. All right, well. Yeah.
Yeah, it's fun. It's really fun. You know, I used to go to the John Bell meetings. John was in charge. John was always, he didn't used to be able to stand up and talk. I'm like,
Right, yeah.
Obama
I hear him.
people was wondering.
I never liked
so much of the fun.
I'm prejudiced against New Yorkers. I'm from New York and I hate them all.
I was around here talking.
They're all obnoxious. I mean, they can't help it. It's so crowded over there.
Just the whole upper echelon
not
of the
just over there,
university.
man.
It's
True,
all
yeah,
the
New
time.
Yorkers are uptight.
Crazy. All the
Yeah,
deans that I work
yeah.
with, just one fell
I was trying to get a better question answer.
Yeah.
Yeah, I'm just wondering if I
Yeah, right.
can get this to stop.
But the rebuilding is occurring. I only got